In the previous session, we have started with the magnetic circuits, and I have already given you the introduction of this magnetic circuits in analogy with electric circuits. Okay, you can just see here I have just listed the differences, or you can make some analogy between the electric circuit and the magnetic circuit. In brief, let me just give you the highlights. In electric circuits, in network theory, you have studied E stands for electromotive force, measured in volts. In magnetic circuit, we come across the term magnetomotive force. Its unit is ampere turn. In electric circuit, the flow is for the current, but in case of magnetic circuit, we say there will be the induced magnetic flux. Here current is in amperes. In magnetic circuit, the flux is in Webers. We come across the term resistance in ohm. Here it is reluctance. Okay, and then you have conductivity, then permittivity. So there are some analogy, some similar analogous terms I have listed here. Now let us start with some basic terms. What is this magnetic flux? So probably the question may be define the following. Okay, these basic terms you should be knowing already. Still, let me just recall it. What is magnetic flux? Phi, indicated the symbol is phi. Number of magnetic field lines, something like psi. In case of electric field, you come across E and the term psi. Psi is the electric flux or the displacement flux. In case of magnetic circuit, you come across magnetic flux phi. It is the number of magnetic field lines passing through a given area. And the magnetic flux is produced. Why the magnetic flux is produced? Whenever there is a flow of current in a conductor, and whenever such conductor we use, wherein there is a current flow, and because of the current flow flux exists, we call such material as electromagnetic. It is not a permanent magnet. It acquires the properties of magnet whenever the current flows through it. The unit of magnetic flux is Webers. WB stands for Webers. And flux का direction भी matter करेगा. Its direction is determined by right hand rule. So even in case of Ampere's law, we have used how right hand rule can be used to determine the direction of current. Okay, then the second basic term that we come across here is magnetic flux density B. We have studied this flux density B already. Still, let me just define it in a proper manner. What is B? It is the magnetic flux per unit area, and the area being normal, kept perpendicular to this flux lines. Okay, and B is given by psi by A. In some of the textbooks, you may find it psi by S. S stands for area. What is the unit of B? It is Webers per meter square. So for each magnetic material, कोई भी जब आप magnetic material लोगे, its property we can determine by this value B. B का value आपको determine करेगा. Magnetization, you have magnetic moment, many properties of any magnetic material we have already studied, okay, in this module. So those things we can determine it very well with the help of this term magnetic flux density. Now, the third term that we come across is magnetomotive force, something like EMF. Here you get MMF. Okay, what is magnetomotive force? It is the ability to produce the magnetic flux. So it is the ability of that particular circuit to produce this flux. And generally in magnetic circuits, the source of MMF is generally it is a coil which carries the coil that has got n number of turns, something like this. अगर एक coil है आपके पास, okay, इसके through अगर current flow हो रहा है, so there exist, sorry, not E, there exist MMF. So we denote it as EM. So what is magnetomotive force? It is the ability of that circuit to produce the flux phi. And MMF denoted by Em is given by N into I. So N is the number of turns in the coil or the conductor into the current that is flowing. So it is directly proportional. The unit of mmf is, current is measured in amperes, N is number of turns. So ampere turn is the unit of mmf. Now, next basic term you come across here is reluctance. It is something like this, reluctance R. What is it is analogous to resistance of your electric circuit. So how you define resistance? It is the opposition offered. So reluctance is also the opposition offered by the coil for the flow of this flux, magnetic flux. Jitna whenever a current flows through the coil, it will offer certain resistance, opposition will be offered by the coil. We call it reluctance. Opposition offered by the material for the flow of flux. And this R is given by, reluctance is given by EMF divided by flux, EM by phi. So what can be its unit? Resistance in electric circuit, we measure it in ohms. Reluctance, you can see the unit, mmf's unit is ampere turn, denominator is in Webers. So ampere turn per Weber. We have one more equation, how we write resistance in terms of rho. You can see, we know that R is the resistance in electric circuit, and R can also be written like this, rho L by A. Rho is the resistivity, or the sigma is the conductivity. So something like that. Even reluctance we can also express in other forms also. So this reluctance can also be written as, this R is equals to L by mu into A. So what is mu? Mu is the permeability of the material. So you know what is permeability, what is magnetization, what is magnetic moment. We have already studied these basic things in the previous sessions. Okay, in the theory classes we have seen it. So reluctance is inversely related to the permeability. जितना material permit करेगा for the flow, okay, for a material to get magnetized, कितना वो permissible है, तो obviously उतना opposition कम होगा. So R and permeability are inversely related, and permeability mu is mu naught into mu R. So I think some four basic terms I've listed here. First one is magnetic flux, phi. Second one, magnetic flux density, capital B. Third, MMF, magnetomotive force. And fourth one, reluctance. So these four basic terms I have listed here. Now, let me just give some basic, I think you have studied these core, okay, core concept. Okay, this is one core, एक material है, electromagnet है. We can say that this as a magnetic circuit. Let's see how the flux is there, how the value of flux can be determined in each of these. We have three different circuits here. So let's see for these three circuits as example how we can analyze. Okay, how we can make the analogy. You can see this is one core. I think CORE core. You call this core or electromagnet. At one end, left hand side, you can see there are some number of turns, right? एक coil है, उसमें current I flow हो रहा है, and these are n number of turns. So whenever current I flows through this, so there will be a magnetic flux inside. So this is produced. Phi. Okay, you can see the direction. So again, we have to go for right hand rule to find out the direction. So this is phi. Current I is flowing through the coil. Coil has got n number of turns. Now, if I want to try to draw an analogous circuit for this, you can see जब भी एक कंडक्टर है जिसमें coil है, एक conductor है which is in the form of number of turns are there in the coil, and some current flows through it. So mmf will be produced. There exists mmf. So that's why I have replaced that with em. And we have flux. There is a magnetic flux produced, and obviously for this circuit, we will be having certain opposition. So even in case of electric circuit also, how you write, you draw one voltage source, then there will be some current flowing, then there will be some resistance offered, right? So something like that, even for this electromagnet, for this magnetic circuit, I have drawn an analogous circuit. And reluctance is given by L by mu into A. And what is this flux, magnetic flux? Flux equals to Em by R. So Ohm's law I have applied here. Phi equals to Em by R. This is one simplest magnetic circuit I have drawn. Now, just compare the second one with the first one. There is certain difference you can observe. Let me highlight that difference. Here there is a difference. There is some air gap at the right hand side. You can observe every other thing is same. There is one coil here which has got n number of turns. There is a current I flowing. You have magnetic flux produced. But there exists a little air gap in between these two ends. So in such case, how the magnetic circuit looks like? You can see because of this portion, I have drawn an MMF. You have a source here, magnetic flux is produced, and because there is a flux, there will be opposition offered by the core. So that is reluctance. Okay, it is not R. You should symbolically draw a Greek letter. So it is RC. Now there exists one more opposition offered because of this existence of the air gap, and that is reluctance due to the air gap. G indicates gap. So you can see the difference between the first circuit and the second circuit. First circuit में सिर्फ एक reluctance है, that is because of the core, okay, because of this electromagnet. But in the second case, there are two reluctances. एक reluctance है, it is due to the electromagnet, which will give some opposition, and the second one is due to this air gap, the presence of air gap, you come across one more reluctance. So since these two are connected in series, so whenever resistances or reluctances are connected in series, what will be the equivalent value? You can see resistances जब भी series में होते हैं, they get added. So similarly reluctances also they get added. So that's why total value I have I have written the total value. See, E by R according to Ohm's law. Em by R. So R is now series value because of two different, the reluctances are because of one is core, one more is air gap. This is the second figure. Now look at the third figure. This is one more magnetic circuit we are going to draw. So what is the difference here? It is something like this. यहाँ पर center portion में ये जो है, this support is common between both cores. Okay. It is something like this. And बीच में earlier in first two circuits, at the left side we have wound this coil, okay, which has got n number of turns and current I is flowing. यहाँ पे whatever coil is there, it is at the center portion. ये center portion इसके लिए भी and इसके लिए भी it is a common beam, okay, that line is common. So if number of turns are n, there is a current I flowing. So obviously there has to be some magnetic flux. So that flux is phi. But see the direction. For this part of the circuit, the direction is in that way, that is anti-clockwise direction. But for the other side, for the right hand side part of this core, the direction of the flux is clockwise. So this is the difference when you have a magnetic circuit looks in this manner, jahan par core, it has one coil at the center portion. So the flux no doubt will be produced, but it gets, the directions of flux are in this manner. Left hand side anti-clockwise, right hand side clockwise. So if I want to draw an equivalent circuit for this, center portion you have coil, number of turns and current. So at the center portion of the circuit, I will have mmf. Okay. And because of this, the core will have certain reluctance, opposition. That. So this is common, and there is a certain flux. ये center portion पे है. But if you see both left side and right side, there are two different fluxes in different directions that I have added. And because the flux values are different in both, the oppositions offered by this part and this part are different. So that I have taken as R1 and R2. You can take any notation. So apart from RC, okay, that is core reluctance, opposition offered by the core, opposition offered by the electromagnet, there exist two more oppositions offered by this left side and the right side. So that is R1 and R2. Now if I want to analyze this circuit, you can see, uh, here this is the flux, it gets divided here. So what is the total flux? Total flux is phi 1 and phi 2. Center portion पे आपको flux phi generate हुआ है. It is split among phi 1 in both left part and the right part. So if you add all together, you will get the total flux. So this is one thing. And secondly, resistances. So how you can write the flux? Flux is mmf divided by the total reluctance. So it is mmf divided by what is the total reluctance. You can see here. I hope you know, you have solved this in the network theory. Uh, how to find the equivalent circuit. Okay, let's not, I will not give you those details. I have written here, it is R1 and R2, these two are connected in parallel. So iska jo bhi answer aayega, that is in series with the core reluctance. So that is your total value. Okay, you try to analyze this, how it is, you are from the network theory background, try to get the equivalent value. So these are some three magnetic circuits I have given you. For first type, what is the equation for flux? Phi. And for second one, where there is some air gap exist, what is the flux value? And for the third arrangement, what is the value of the flux? Phi. Okay. So this is what is all about the magnetic circuit. These are some basic equations I have written. I don't know whether they are useful or not, but we have already used these equations. That is for sure. B equals to mu h, then del dot B equals to 0, del cross H equals to J. Because I have listed them because it is already listed in your Haight and textbook, Haight and Buck textbook, along with this magnetic circuit topic. So I have listed it. You can just go through the equations, how you find the total current I is surface integral of J dot ds. We have used this even while solving the problems also. What is the total magnetic flux? Flux phi equals to surface integral of B dot ds. In the previous session, while dealing with the normal component, we have taken this equals to 0. Remember. Okay. Now, the next concept is important one, energy stored in a magnetic field. Okay. If I want to give you the analogy, आपके पास एक कंडक्टर है in the form of a coil, suppose. Okay, coil है. If suppose some current I is flowing through this, because there is a flow of current, there exists magnetic flux and magnetic field lines, right? Both will exist. So because of this concept, when there is a coil, conductor है, उसमें current flow हो रहा है, because of the current flow, magnetic field exists. Because of this, there exists flux. For this complete arrangement, we come across the term energy. So you know already, you might have used this in your laboratories. The basic components, resistor, capacitor, and one more is L, that is inductor. Okay. So what is an inductor? I have written here, I think you can see it. Similar to capacitor, inductor is also energy storing element. So capacitor, what for you use it? Capacitor for charging and discharging, right? It stores the energy. So similar to that, when we come across magnetic circuits, inductor is one such component which will store the energy. So it is a energy storing element. So whenever we talk about energy in the magnetic field, inductor will come into picture. Fine. So let us see some equations related to the inductor. Let us consider a coil. You can observe here, यहाँ पर एक coil है. Okay, some number of turns are associated with it, say n number of turns, and there is a current I flowing through it. So let us consider a coil of n number of turns as shown, through which current I is flowing. When I think you already know this phenomenon, क्या होता है जब current flow होगा, flux generate होगा, and जब current change होगा, flux को क्या होगा? I think this concept already you have studied. You might be knowing even about back EMF concept. Okay, just I'm recalling those terms. When the current I builds up in a circuit, so you have some current I is flowing through this coil, there will be a magnetic flux produced in the coil. Number of turns hai, current hai, so current hai, there will be the field and there exists magnetic flux. Okay, this is what, this is the inherent property of that material. जब भी current flow होता है, field रहेगा surrounding it. जब ये process होगा, flux will be generated, flux will be produced. So now this is what the property. But what will happen? Just a second. When, what will happen? See, when current flows, this phenomenon occurs. Field create hota hai surrounding it. Okay, and we have even seen how the field will be created. जब भी एक solenoid है, okay, example, let me take a solenoid. So how the field lines exist, try to remember. In during the class we have we have done some derivations also. जब center portion through the coil hoga, straight line, the field lines, the flux lines will be restricted to only this center portion. Coils, this circle number of turns ke through jayenge, and after that something like this they will divert. Okay, so this is the phenomenon that occurs. It is due to the inherent property of the inductor. Okay, but what will happen when we change the current? जब current flow का magnitude change होगा, when the current I changes gradually, so obviously field change होना चाहिए, then field change होगा तो flux change होना चाहिए, right? This is what should happen ideally. But what will happen is when the current changes slowly, gradually, the magnetic flux which is associated with this coil, क्योंकि coil में number of turns होंगे या number of turns, so obviously magnetic flux change होगा. But you know, in nature, whenever there is a change, there is an opposition. Okay, that's a general rule, a general everything tries to remain in an equilibrium position. आपको मैंने example spring का भी बताया था. Whenever you drag a spring, it will oppose that. It will oppose how it will give you what? It will try to attain its original shape back. So everything in nature tries to remain the equilibrium. That is the nature. So that's why whenever a current uh, changes gradually, flux भी change होगा. जो भी create हुआ है flux, that will also change. But what happens in the coil is, because of this, जब flux change होता है, there exists a creation of back EMF. So ये क्या है? Opposition है. Back EMF is what? Opposition. Back EMF is produced in the circuit. So if I want to write it in the form of an equation, how I can write? EMF produced, back EMF, it is directly proportional to di by dt. In the sense, जितना current change होगा, gradual increase. Okay, यहाँ पर plus है, indicating that it is increase. We are changing the current gradually. Flux change होगा. जब flux change होगा, EMF produce होगा, back EMF produce होगा. So E is directly proportional to di by dt, change in the current. So if I remove this proportionality sign, make it equal sign, there will be some constant. That constant, let me denote it as L. We call this L as inductance. Okay. I think again inductance may we will learn, we will study what is self inductance, what is mutual inductance. Okay. So this you remember, जब भी current flow होता है, field create होगा. Because of the magnetic field, flux will be there. And flux किस पे depend करेगा? Number of turns पे depend करेगा. However, जब आप current change करोगे in the coil, when you start changing the current slowly, flux will also change. Because of this, a back EMF is produced in the circuit. And that is directly proportional to di by dt. E equals to L di by dt. I think ये formula आपने already पढ़ा हुआ है. E equals to L di by dt. How I have got that? Just side में मैंने लिखा है. You can see this EMF is actually E is equals to N d phi by dt. जितना flux change हो रहा है, and because flux is associated with number of turns in the coil, I have multiplied that N into d phi by dt. So further, I have multiplied and divided by I on both sides. Then I'm exchanging these two things, keeping N I, sorry, not this I, phi, N phi by I. There is N, there is phi, there is I. All together at one side, remaining di by dt outside. I am calling this all N phi by I as together L. So there is one, so just I have written this. We will be using this in the later concept, inductance concept. But let's not bother about this as for now. Just remember that whenever current changes, flux changes. Flux change होने की वजह से inside the circuit there will be the back EMF will be produced. Now, inductor opposes the change in the current value. Back EMF, I said, it is the opposition. Okay, it is the opposition. That's why inductor will start opposing this change जो आप change कर रहे हो current का value. Why this happens? Why inductor will change? Why inductor will oppose? Because of its inherent property of inductance, that is called electrical inertia. Because of this, just something like spring. Spring जब आप खींचते हो, what spring will do? It will oppose that change. It will, in return, it will also give some back. What? It will try to regain its shape. That is what? Because it is its inherent property. So वैसे ही inductor का inherent property है कि it will change the, it will oppose the change in the current value. Hence, a work has to be done in order to force the current through the inductor. So that's why जब inductor oppose करेगा, so the current flow will be a bit difficult. That's why certain amount of work has to be done. You have to spend some energy in order for that current to flow through the inductor. So that's why the heading is energy stored in the magnetic field. Okay. Whenever energy concept comes, inductance will come into picture. So work has to be done in order to force the current through the inductor, and this energy, it gets stored in the magnetic field. Fine. So we will see what is that energy. Suppose a small amount of work is done in moving the charge per unit time. Charge per unit time is current, right? Charge in moving a charge per time. If I symbolically denote it as small work dw, so dw with respect to the time is, you can see vi, e into I. Work done is equals to e into I. This is from the basics of physics. Okay, work done with respect to time. okay, is equals to E into I. So what I have done in the next step, dt I have taken it to this side. Okay, then further I have see here for E I have substituted some value. Yeah. E is equals to L di by dt. So let me substitute that. E equals to L di by dt. I and dt I have kept it as it is. So what is dw? I think dt gets cancelled. You'll be left with L I di. So this is the small amount of work done. What for the you are forcing the current to flow through the inductor. वो force करने के लिए इतना amount of work done आपको करना होगा. So if dw is the small work done, to get the total work done, we have to go for integration. Okay, integration जितना current flow हो रहा है, for that particular current to completely make that current to flow through the inductor, that is 0 to I have to do some work. W will be ये जो भी है L I D I, इसको integrate करना है. So the integration is with respect to I. Di is the variable. So L is constant. I have kept it outside. So it is I di. What is the integration of x? Integration of x is x square by 2. So it is integration of I is I square by 2 for the range 0 to I. Okay. So it is half Li square. This is the work done that is stored in the magnetic field. Whenever the work done concept comes, it means there exists certain opposition by the inductor side जब भी आप current change करो. Because of this opposition, इस opposition को you have to cross it and you have to do certain work so that the current can flow through the inductor. So that W is given by half Li square. Now a small concept is remaining. Energy density. So what is energy density? Density means what? Per unit volume. This you know. Density is mass by volume, right? So energy density means energy per unit volume. So suppose इसके लिए भी एक equation है. I am taking this energy density as capital U. If I consider a solenoid with n number of turns, which has got number of turns per unit length. Say solenoid है. If I just divide the complete solenoid into number of parts and if this is per unit length, so इसमें जितने भी turns आएंगे वो आपका n होगा. Okay, ये भी small amount of n. So अभी आप सभी n को add करोगे तो आपको total number of turns. Now suppose fine, U equals to what? Energy per unit volume. So energy or work done अभी हमने पता किया है, it is half Li square. Let's see what is energy density now for this solenoid. Okay, we know that for this solenoid, self inductance value is L equals to mu naught n square A into L Henry. We will be studying this, deriving this L in the next concept. ये L का equation हम देखेंगे for a solenoid. Now presently you take this as, and this is L. What is energy density? Energy density is energy divided by volume. So work done is equals to energy, right? Work done, that's energy by time is work done. So per time ही हमने calculate किया है. So that's why work done W I have taken half Li square. V is the volume. So volume I have split as area into length. L into L is volume. L into L is area into length. Area into length is volume. Again for a solenoid, what is L? Mu naught n square AL. So I have substituted that here. AI denominator as it is. ये दोनों cancel हो जाएंगे. U is half mu naught n square I square. So what is U further? Since here we have square terms, let us take mu naught also square. उसके लिए I have taken numerator and denominator. I have multiplied and divided by mu naught. So that ये दोनों को club करके I can put mu naught square. So if I reduce this, U finally I will get it as half mu naught H square. So this is energy density. You can just